All right, we are talking work in its simple vector format. We're not going to deal with variable forces yet. All right, so what is work? Work is energy transferred into or out of a system by external forces. And work is also the force times the displacement. But we do need to be careful with this. It's actually the force that's aligned along the displacement. Forces that are off axis don't count for anything. So it's a very important point. If there is no force, there is no work. So in the absence of external forces, there's no work done on a system. It is also true that if there is no displacement, then there is no work. That is important. So the common definition of work, the one that you're probably most familiar with from the way it's used in day-to-day life, is not physical work. So, I was sitting and typing at my keyboard, typing in programs, and I worked really hard today. Well, I mean, your fingers worked a little bit, but you didn't do a whole lot of physics work. You did do a lot of mental work. It's a completely separate concept from physical work. So physical work, there must be displacement in response to the force in order for there to be an actual work component. All right, enough with definitions. Let's give the equation definition. Work is equal to the force times the displacement cosine of the angle between them. So if the force points at an angle relative to the displacement, if the displacement is horizontal and the force is at an angle, you'll have to find the component of the force that's along that angle and take it together. Alternatively, work is equal to, in proper vector form, the force dot product with the displacement, with force and displacement both as vectors. These two equations are functionally the same thing as long as you think about the magnitude of the force and the magnitude of the displacement. So the magnitude of the force vector times the magnitude of the displacement vector, their lengths, times cosine of the angle between gives you the work. Or the work is equal to force as a vector dot product with the displacement as a vector. On rare occasion, you will be given sufficient information to handle it with the dot product and I hat, j hat, k hat. More often, you'll be finding the magnitudes and the angle between them, and then you'll be working out the magnitude of the force times the magnitude of the displacement times cosine of the angle between. Okay, again, if you're pushing against a wall as hard as you can and the wall doesn't go anywhere, you have not done the standard physics work. You haven't done work on the wall. The wall also hasn't really done work on you. You will notice you'll get tired, but that has to do with some interesting work things that are going on inside your muscles. It sort of attempts to move that fail and end up using energy in the process, but it's more of a chemical thing. It is physical, but we can't see it. It's too small of a displacement. Anyway, that's just coming from my background. I studied kinesin and dynein, which are molecular motor proteins, in a biophysics lab. And in muscles, there's a similar protein called myosin that runs on an actin framework, and all the stuff that happens with it is very interesting. Basically, it turns out we all have little motors that walk along tracks inside of every cell of our body. And they're responsible for all kinds of things like the contractions of muscles. Okay, and a lot more than that, but that's kind of the one that's most obvious to everyone. All right, these are the definitions we need. Next up, we'll be trying problems. I don't know that there will be videos ready for you this semester, but those of you watching in future semesters may find that there are a few videos following this one that show you examples of using this method to find the work. All right. this was short, so we'll stop here and go try some problems.